So I'm Jason Ward. I'm an assistant professor at NC State in the Bio and Ag Engineering Department. So today I'm going to talk some about some of the tools we use to detect crop physical damage with UAV systems. I'm not sure why I'm wedged between two LiDAR talks. I use some LiDAR data in our pipeline down the road, but I typically use some other techniques. But let's go ahead and get started and see if we can get through all of it. So the big thing we need to remember here is that primarily when we talk about UAV data collection in ag, there's really kind of two major modes that are going on. One is object detection. So that would be mainly for population counts. Yeah, let me do this. This sounds a little bit better. That's mainly for population counts or counting plants when they've just been planted. There's also vegetative indices, right? So mainly they're going to be looking at plant stress and water stress or nutrient stress. So those kinds of things are typically the two major places that we use UAV data. Why there? I think mainly because they're the most inherently actionable. They're the places where people can respond to it. They're also places where inputs and solutions can be sold to end users, right? So that's kind of why we wind up with a lot of work being around that space. So the questions I have are, can we use these same tools and techniques that we use through the mid-season to inform harvest decisions? And what does that really look like? So I kind of got to this question by looking at some work done by my colleagues in Ohio who were looking at multi-hybrid planting systems. So this is one field that's planted in two different seeds of corn. And the idea is that they can target high productivity areas with a more aggressive variety, or you can target defensively and plant a plant that you know will always make no matter what the conditions. So this is two different varieties in the same field. But something interesting happens. Whenever we harvest this corn, it may not all be at the same soil and at the same grain moisture. And that's a big difference. So if we look at a study we did previously, we can see that even all the way down here, whenever we're 121 days after planting, we've got some pretty big differences in moisture content. Anything above 5 percentage points of moisture, your yield data is going to be compromised. How you harvest, the harvest performance of that crop will not be the same, and your storage decisions will not be the same. Right? Because if you have a high moisture grain, it will decompose a lot faster than a drier crop. So there's a lot of things here that go on that we need to be aware of. But what we see is kind of what we expect, right? After maturity, we see a good kind of linear dry down. Basically, we see that the rank is about the same, right? And every kind of day after planting, the same hybrid is the same min and the same max. So that gives us an idea of what we're looking at. So whenever we first realized there was this variability, we said, can we detect it? So we actually went in and just did some simple thermal imagery, kind of did everything as wrong as we could just to start drawing the box around this issue, just to see what we could actually do. So we used a really cheap FLIR Tau 2, the simple 8-bit, and since it's a rolling aperture, we had to get all the plots in one image. So we had to go all the way to the ceiling to get that image. So we pulled it all in QGIS. We did some simple zonal stats, buffered everything in 0.5 meter, and the mean values for those plots became what we analyzed on. So what we saw from the mean digital returns were that generally, the later in the season is when we saw differences in that thermal image, but we also saw that generally there was one that was lower in thermal than heat, right? So that means the top of the plant was cooler. That means it's still respiring. That means it's still pulling water and it's still working. And that rank kind of maintains, even though there's a little bit of shift in the values. What happens, though, when we compare that to the actual moisture content that we measured of this grain crop, we start seeing that there's a little bit of a pattern here. That the maximum moisture content equals the minimum thermal value over the flights that we saw significant differences. So we started realizing, well, there's actually things here we can detect remotely in the late season environment that can give us some insight about how that crop's doing. Well, so then kind of in a summary of that piece, we saw that we can actually use this low-res thermal imagery. We get better as we get later, and we could actually start seeing some additional variety and hybrid effects in these values. But we realized, too, that that's not the only thing we need to look at late in the season, right? Especially on the coast, what we see is that harvest season
is hurricane season. Okay, so we know that those crops, after all the work has already been done, after all the time, all seed, diesel fuel, labor, all those things have already been invested in that crop. During hurricane season and harvest season, they could lose a vast majority of the value of that crop. So we need to be able to detect that. With Florence and Matthew this last year, we lost over $1 billion worth of value in agricultural commodities. So we need a way to detect that. We need to catalog it, classify it in a way that makes sense. So when I think about a stakeholder for this kind of product, there's really kind of four major groups, right? So we have a producer, farmer. He needs to make a decision, he or she needs to make a decision about what he wants to do with that field. Okay, do I need to harvest it, or do I need to salvage it, or do I need to let it go and claim the total loss? Similarly, the insurance provider is a data user. Disaster response agencies, because the ag data gets collected into the total value of damage that goes up the chain to get different disaster declarations made. And stats agencies like NAS or other similar agencies would need to know about the crop damage. And I also want to point out this is not just severe weather. So these are images of bear damage in cornfields in eastern North Carolina. So we can actually, once we get the algorithms figured out, we should be able to detect most types of physical damage that would occur to a standing crop that we could then start cataloging and classifying. So we actually went out into a field, which was difficult for me, and we broke some corn. Okay, so this perfectly beautiful field of corn. So we went out and broke some off at the ear and stomped it down at the ground. It's basically to simulate two different modes of damage. One would be like an acute wind event, and the other one would be like a wind event after a soaking rain that would cause the entire plant to break over, okay, or to lodge. We did that over 5 or 6 weeks. We started 2 weeks before the relative maturity of that crop, and we went 3 weeks afterwards. So we can kind of see what happens over time and the time effects of that damage and how that changes our analysis. So we put a DJI M600 over it. We flew a Zenmuse XT with both RGB and multi-spec in the NIR band. We did all of our data processing in Precision Mapper. So just to give you an idea of what this looks like then after the fact. So on the top, you'll see some color imagery. I think that it's really important to do as much as we can in RGB, right? It's the most accessible. It's the one that when somebody looks at it, it makes the most sense to them. And there's a lot of things that we can do with vegetative indices and with different reflectives that we can do with just RGB. And then finally, we do have multi-spec if we want to calculate representative values of essentially the greenness of that crop as reflected through the chlorophyll reflection. So we got 2 different major bands. And what's interesting is keep an eye, see how there's already some variation between green and non-green areas in this field. They'll see them pretty well on the NIR. Keep an eye on that because you'll see that come up again a little bit later. So there was already some pretty good variation in this field. So what you see there are the first 2 treatments that we installed on that field. So literally we went out, we had 2 treatments. This was the first week. So we broke this one off at ground level. We came out and we broke this one off at just under the first ear. So these were 6 rows by about 100 feet long. Okay? And you see the ground break on the left and ear on the right. Again, keeping an eye on that variability. We went out for the last flight. Now you can see all the rest of the treatments that were installed every 5 weeks progressively after the first one was put in. So what we have is essentially a long strip plot design, and we're kind of repeated so much in time rather than with plots. What's interesting, though, if you look at this picture, you see the areas that are green and the areas that are less green. If you go late in the season, those are flipped, right? Because the areas that were less green, weeds were allowed to flourish in those areas because there wasn't enough competition from the cover crop there to keep them stymied. So you can kind of see we wound up with some interesting weed bands. Kind of looks like a big handprint across the field. So we're kind of calling it the devil's handprint here lately, but because it made some trouble for our analyses. You can also see between the first and last flight here where the weed pressure came in specifically in the plots where we broke off at ground level. So this is the first treatment that we put in at the first flight, and this is that same treatment at the last flight. So we had a lot of grasses emerge when they exposed ground there, which is not necessarily surprising, but it's just something we have to be able to handle in analysis down the road. In addition to the raw imagery, we also converted a lot of that to structure from motion to get some digital surface models. And we did actually fly this with LiDAR as well. And so we're ingesting all that data now and really starting to compare to see what we can get by with in terms of, can we just use the SFM, or do we really have to go LiDAR level data to get this at scale? But yeah, so it gives you an idea. You can see the differences. This is a ground broken one. This is an ear broken, and in between are alleys that were left standing. So you can really kind of see that detail pretty plainly. So you remember talking about those different fingers and the weeds that were showing up? So if we look at from the first flight to the last flight, our control plot actually looks pretty similar. But something interesting happens. If you have a very low NDVI and then you come up in time, that's that weed effect, okay? When all the rest of them declined over time or stayed relatively similar. Okay, so that's just saying that we can't just keep brute forcing NDVI and expect to get a usable value out of this, right? We can't just keep shoving a satellite indice from the 70s onto cropland and assume it's going to work. So we have to be a little bit smarter about what we're going to do. So in this area, what can we do now to make the analysis more accessible, right? So if we can downplay this to RGB only, we've essentially taken all the additional secondary flights or secondary vegetative indices out of the process. If we can also reduce what the user level analytics are, okay, so if we can actually make it to where somebody brings in a shapefile or something of a field boundary and then drop in over this imagery, it'll automatically say this % of your field is damaged and this % is not damaged, right? That's ideally what we'd want to see. Well, you start looking for solutions. And you're trying to get grant dollars and you find something kind of buzzy, and that's artificial intelligence, right? So that's kind of gives us a tool that we start looking into to start detecting this crop damage automatically. So just to keep it fresh in your mind, remember that all machine learning is artificial intelligence and all deep learning is machine learning, which is artificial intelligence, right? So just kind of keep that in mind. So the thing you have to remember, that machine learning is where you just give something a set of rules and a set of outcomes. It's kind of like if you played checkers against a computer, right? So it just knows what the rules of the game are, and it knows it doesn't, if you wait a move to not lose its piece, then it's not going to make that move, right? So it knows the rules, but it doesn't so much know it's playing checkers. If you are talking about machine learning, then you give it essentially data, and it extracts relationships among that data. And typically in deep learning, you'll give it an image and extracts relationships to the tables, and then extracts relationships on top of that. Okay, so if you think about object detection, we have to create that class of object, find it in the image and draw the box around it. So we kind of train this model to look for these things that are in a picture, right? Generally, it's all rectangular. So when you're dealing with plots in a study, that's kind of easy. If you're dealing with data in the real world with the real crop damage imagery, that won't be so easy. So we'll have a little bit of effect from the training models there. And this is what you're doing when you're doing the CAPTCHA, right? Whenever it says, click every picture with a fire hydrant in it, right? You're training Google's AI model to look for those things, right, in its imagery, okay? Just keep that in mind. You're working for the machine now. So, if we look at these objectives, really what we want to do, we want to fly and get this stitched orthomosaic for our field. Because the models that we use for deep learning actually only work on square images, okay? That was a new one to me. I was not aware of all the restrictions around it. So we actually go in and then we sub-segment the stitched imagery again because the raw images that we took are not square. And so we actually go in and we grid the ortho, extract the images, and that's what we run our training data set on. So we go look at every image and say, is there in this zone something that's damaged or something that's not? I'll show you like an example of that here in a second. So we train that object detection model to look for damage. Now what's so great about machine learning and deep learning is that we don't have to tell it what it's looking for. We give it the outcome. We say this pixel is different from this pixel and you figure it out and tell me why, right? Or just help me classify it. So we don't have to drill into it and extract a lot of additional information about it. And so then we want to test those models. So what does training look like? So in this case, this is a picture of a wind burst damage that occurred on some sorghum. So we would go into this model, to this image, we would highlight areas of damage and areas of not damage, and that becomes the basis that the model then runs on. So it looks at those pixels that we've classified, starts doing comparison between the two, extracts a relationship, and then moves forward. I never thought I'd have to say the words YOLO in a professional setting, and I'm sorry about that. But some of the object detection models that we are using are YOLO, Faster RCNN, RetinaNet, and TensorFlow. So the first two, we've already created all of our models for all of our different flight dates. Okay, so we've collected them, we've got very good performance, we've seen very good incremental improvement in the model as we feed more and more images into it, and that's what you want to see. If at some point the accuracy starts decreasing, then you've kind of saturated the model, okay? So when I say HPC, what I'm talking about there are high-performance computing. So we have a core facility on campus at NC State that's got multiple GPU nodes on it, so we can send processing jobs out to it and let it do all the heavy crunching instead of having to build supercomputers in all the departments, right? So we have a central facility that does that. So YOLO is the one we've been using the most, and I'll show you some results from it. RetinaNet is Facebook's AI, right? So the thing that whenever somebody puts a picture of you and says, oh, is this Jason Ward? And you say yes or no, that's RetinaNet. So we're actually trying to extract something useful from Facebook so that we can use it in a good way. But yeah, so we're still working on RetinaNet. We're not there yet, and we have not had any luck with TensorFlow, which is Google's primary AI product, or their object detection product. Okay. That's unexpected. Okay, all right. So, preliminary model performance. So I showed you the imagery we collected from our first flight from 2 weeks prior to relative maturity. And so after we have fed in thousands of training images into it, and then we show it an image it's never seen before, and we say, find the damaged areas in this picture. And so what it does is it highlights the areas it thinks are damaged, and then gives us a representation of how sure it is that it is actually classified as damaged or undamaged. So we've got, it's highlighting that first plot that we broke. It's 63% sure that that's actually damaged area, field area. In the other plot, 66, and there's kind of an area in between, about 44. So it's our job to say anything over 2/3, we'll say it's damaged, right? So we kind of got to go in and set the thresholds for surety on these calculations. But it's actually for the paltry amount of data that we fed into this versus the results that we got out of it, we're actually really encouraged. We think we can do some interesting things with this going forward. And as we continue to feed more and more complexity into it, it gets a little bit harder for the model to detect, right? If you add more artifacts into the data. So in this case, there's really no damaged area out here, but it's still detecting it. It's kind of under detecting over here, and then everything kind of starts stacking up. But so that's kind of to be expected. So we have to start doing a better job of figuring out how to extract what it's classifying and start comparing it to knowns to start getting a better performance measure on it. So whenever you start kind of lining it all up, especially here late where there's a lot of damaged areas, things start getting a little bit hectic. So we're still kind of working through the best ways to ingest everything that's coming out of this model and to make it more actionable. But like I said, for one season's worth of data that was not really replicated spatially, it's not too bad, right? So we think that right now our ability to automate crop damage detection at scale is promising using only RGB imagery. But I think if we add additional data sets to that, like a post-disaster flyover from a LiDAR aircraft, we think that it could be very interesting as an additional check for that detection. We're continuing to compare different models. So we're not software engineers, so we're not developing all these codes. We're really pulling them in and leveraging them into our space. So we are just kind of chugging through them and seeing which ones perform the best. We're working now to amplify our training data, so we'll be getting additional imagery this next growing season. And there's techniques that we can do, like we take that tile that we trained in, and then we start twisting it by 5 degrees, right, and reloading it back in. All right, so there's things we can do to multiply the data we already have, or we can add noise to it or change the hue, saturation, or brightness of different color bands and feed it back in. So there's things we can do to amplify and multiply the data that we already have. So yeah, so we're going to be repeating this study with a more formal structure now that we have seen some results that come out that give us some hope for the future that we could actually do this and bring it live. And we'll be moving forward with that this next year. So with that, 30 seconds to spare. My name is Jason Ward, NC State. I run the Advanced Ag Lab there in the Bio and Ag Engineering Department. With that, I'll be glad to take any questions you might have. Yes?
I noticed your test field has some water stress areas on it. Is that confusing your AI?
Yeah, so the question is that the test field had water stress areas in it, and yes, that is confusing our AI because it's not, that area is brown, but it's still not damaged. Right, so whatever it's looking at, it has to get more advanced than just the color band, right? So yeah, so we have to show a diversity of undamaged crop that is both green and brown and those kinds of things. And what's interesting is, especially as that same, if you drew a box around that field, as that same box progressed in time, that crop color would change. Right, it would senesce, it would start dry down, it would look more blacker than browner. So we have to get smarter about how we build those models. Yes?
Scalability and time, this is fascinating stuff, but it's a test on a small scale. When do you perceive this is going to be something that's going to go nationwide, Department of Agriculture just zaps everything and goes, what's happening?
Yeah, so the question is about scalability. Really, the key there is once we build the models, we can actually push those out to existing either Amazon AWS platforms or Microsoft Azure or Google. They already kind of have the ability to do that live now. So we just need to build the appropriate model and push it out. And then at that point, it would be spinning up the servers whenever we would need to collect that data. Right. And so that's the challenge too, is actually the imagery collection piece. So, if we're trying to think about this in a post-disaster environment, there may be already some of the imagery coming in that we could leverage, or we might expect to see some enterprising UAV pilots, out there getting it. So that's kind of the logistics piece that we're looking at next. So along with the technical side, we're actually pulling in FEMA, Farm Bureau, NAS, all the stats agencies, kind of grower representatives to kind of ask, what would it take for you to be comfortable with this data, right? And kind of asking that, are you okay with after, having somebody hand you a disaster report that says, well, this is how much of your field's damaged on your farm, surprise, right? So there's some things we have to do about comfort and usability with that data and understanding all the sociological aspects of it. Yeah, but definitely just the sheer logistics of getting the imagery are still a challenge. Sure.
So I guess at some point you're going to be testing this in the real world, what the yields and what the predictive ability to predict things happen and get back to check. Have you got that far yet?
That's the next step. So kind of if you think about it, we started with the sensor, right? And now we're starting to get to the edge of scaling it out. And what we can really do is if we can get to the point where, let's say we've got a pretty good idea of the rainfall and wind speed all across the coast, right? And we spot check some of those areas with this algorithm to detect crop damage and actually compared it and did a good validation check with that. Then we may not even need all the imagery and the AI behind it. If we've got a pretty good model that says if you've got corn at 120 days after planting, it saw this much wind and this much rainfall in this soil type, then you've got a pretty good chance of the damage being this. So if we could actually start scaling it out, but we still need to be able to get to validate that data set at scale first. Yeah.
Have you thought about seeing if you could reference this to, say, the Planet Labs 3.5 or 2?
Yeah. So that's exactly where we're going next, is try to leverage those existing data sources. Yeah. But we haven't been down that road yet. Still just trying to get the core relationships built first. So, yeah. Oh gosh, yeah, sure.
Are you doing a comparison between like the AI and just like an image classification?
Mm-hmm.
Just sort of saying, seems like image classification gets you pretty far along.
It does, but yeah. So the question was if we're comparing AI to image classification. But yeah, I think the image classification would get us there. But then you have to have the ability to look at that underlying data and then interpret it, right? So if we can go to the AI and it just says yes or no, and we say it was right or not, that's kind of a less of a technical expertise in the field. The technical expertise lives in the hard drive. Yeah, sure.
Also, you had collected elevation data, I guess, with the plot. I mean, it seems like that information would be a huge help to the AI to classify things. But is that just too much of a hurdle to collect that along with the imagery? Or? No,
because it'll drop out of the orthomosaic imagery, even just with RGB. And it needs to be properly ground referenced, to get high quality out of it. But that's definitely one of the additional data sets that will go in. We just kind of wanted to feed it the least amount of data first to see what was there. But absolutely. So what would happen is there might be an index that would pull from both RGB and the digital surface model at the same time to kind of output a crop damage index. Yeah, after that. Yeah. Okay. Sorry. I'll be over here for a minute.